Okay, so I'm going to flip back to my slides here and say, the direction that we went from this is to go from working on a single data science virtual machine to working on batch AI. I'll tell you a little bit about what batch AI is. I'm sure most there'll be some equivalent on other cloud providers as well. So what is it? It's just a utility to help you create GPU clusters. We're not charging anything extra for it. It also works as a job scheduler, so that you can line up a lot. Say you want to do a hyperparameter sweep with a script you've just developed. You can submit these jobs and pull out the results later. It's a pretty handy utility. You can use it in a graphical way if that's your preference, but typically we're using this from the command line. And it's also possible to build it into other applications using SDKs. So you have a number of common programming languages available there. You can even have scripts that you're developing inside of an IDE like Visual Studio be launched directly onto that remote compute to be run on your GPU cluster. So there's some handy add-ons for this service. I think you will discover whether this is something that just adds overhead to your life. Once you reach that point where you've already tried 4 GPUs and you want more, maybe this will be worth the investment for learning this particular system. But so I'm going to tell you a little bit about the nomenclature here. We have a notion of a job. This is a run of a script. We assign it a unique ID. And we make sure that all of the files that it writes out have no way of overwriting anything else that you've done. So if you perform multiple runs, you're not overwriting the same file on disk. You'll always know what commands you ran, and how that associates to the model files that you produced. That can get pretty handy after you're doing a lot of minor debugging in a script or like a sweep for. So that's pretty nice. Jobs we organize into things called experiments. And the reason that we do this is, typically you create a cluster for exactly the amount of time that you want it, and you delete it afterwards. You don't want to pay anything extra for compute, right? You don't want to leave it around and come back the next day. And so you don't want to have these job files stored on your actual compute, on your cluster. So what the experiment helps us do then is store that as we create new clusters and delete them. So finally, we have this notion of a workspace, which just lumps all that stuff together, experiments and clusters, where you can go in and navigate and see what you've got. Okay, so I'll show you in that repository that I mentioned earlier. So this is the pixel level land classification repository that you briefly saw on your screen earlier. That this thing is organized into 2 components. One is a set of things for the GeoAI DSVM, the notebooks that you just saw. And then we have the batch AI components. So this describes how you would create the commands you'd use to create the cluster and run exactly the same training job, but now on the cluster instead. And that's designed to help you see what, maybe get around the onboarding process for this new service by having seen an example before. So I've already gone through these cluster creation commands. I'm going to give you an idea of what that would entail. So yeah, this can be done, like I said, graphically, but here are the commands for doing it from the command line. So we use a utility called the Azure CLI. We have versions for Linux, Mac, Windows. If you're using a data science virtual machine, this is actually installed in advance. So pretty handy utility. And the equivalent, AWS and other cloud services have an equivalent. So we log in, we make sure that we're using the right subscription so we aren't charging the wrong people for the resources that we create. And then we're ready to go. So we want everything to be kind of lumped into one place so that we can easily delete it when we're done. That way you're not paying any extra money. So we create this resource group. And then everything else that we create gets dumped into that. Think of it as a directory inside of the cloud for storing all the resources that you want to delete together. We create a Azure storage account. This is where the nodes in our cluster are going to look to access the training data, and also where they're going to store, in some cases, some of the output data. So in this case, we have this command to describe what type of account we want to create, what we want to name it. We also want to store out the account key. So we're going to use that subsequently in our code. So we have this rather strange-looking command. What this is doing is taking the output in a JSON format and querying it to get just the key back out. We create 2 different types of storage here. So maybe I should actually pop back to my slides. I've got a little slide on that. Okay, so the choice of storage that you use can matter a lot for the training time involved, so how long it's going to take to read that data, and whether you can stream it. So we have an option called a file share. This is sort of our slowest option, but what it does allow for is reading files that are still being streamed. So if you have logs that you're still writing, this will help you, this storage option will let you do that. It's also great because it can be mounted on Windows, Linux, or Mac. So if you are in the process of debugging a script, you can have it open in your IDE locally, editing it, and that will be affecting that will be the copy that the cluster has access to as well. So as you can see, this is not something we recommend for accessing data during training because of its slow speed and because there's a 5 terabyte limit. The default that we do recommend for training on these clusters is storage on blob. So you have effectively no file limit here. It's well into the petabytes. The relatively fast concurrent access, so we've used this up into the maybe dozens of workers. And you can still mount this on Linux if you like to easily transfer things, or we have all of these clients to make sure that you can transfer files quickly to that storage in parallel. So you should have no problem getting your data there and getting it back off again. If you do need to have a very large number of workers, and in our case I'm going to show you an example where we used up to 148 GPUs working on our training data. Then we have these, so we have network file service, cluster FS are some options that you can use to have a little bit more control over what is happening on the back end to store your data. So NFS is a managed service, but Gluster FS is more construct your own, but we support that choice if you like it. And finally, the fastest option is to make sure that the data is available locally on the VM. So if you are able to have as part of your cluster setup, transfer the files that each worker will need locally, that's great. The only thing to keep in mind is that you're then limited by space. So you've seen that these scratch drives typically have a few hundred gigabytes. It's more if you provision with more GPUs, but you get the idea. So that's the options that we have available. And in this case, for our example, we're using file share and blob. So we create a file share, we create a blob storage container, and we start copying files over. So that, again, we're using AZCopy. This is that same command that we used in your notebook to transfer training data to your data science VM. Now we're using it to transfer data to your new storage account. And it's the same data. You'll recognize the URL if you go back and compare. So it would take a few minutes to run, as it did for you. And then we create the resource types that are specific to batch AI clusters. A workspace to contain our experiment and cluster, the experiment, and then the cluster. All right. So the cluster we have a definition for. So let me see. I think I have that handy here. Okay. So in this case, it's a very simple JSON file. In fact, you don't need one of these at all if you're just creating a standard VM. But in my case, I want to install a few extra packages that aren't there by default. So I don't have TIFF file in there by default, and I want to read TIFF images. So I'm going to have every VM in my cluster run these few commands to install things like TIFF file. I also, while I'm using a data science virtual machine image, now I'm not using the GeoAI data science virtual machine anymore, because we only have that available for Windows. And Batch AI assumes an Ubuntu background. So I'm going to install things like all these geospatial libraries that we used before. Okay, and you also see that there's a path. Basically, it's going to write any errors that it encounters during cluster setup to my file share. Okay. So I run this cluster setup command. It takes maybe 5 minutes, depending on the number of VMs, I suppose, to say 5 minutes to provision that. And then I'm ready to start submitting jobs. So I already have this cluster created. And I've run these jobs before. Let me show you what it kind of looks like in the portal. Okay. So again, the portal is our graphical interface. So switch back. Okay, so I have a resource group I created. The resource group contains the storage account, the workspace, and inside of the workspace is an experiment, and also the cluster. Okay, so if I click on my cluster, you can get some idea of how much use it's seeing. Right now it has 2 nodes, so it has 2 nodes each with 1 GPU. Probably a better strategy to use as many GPUs per node as you can, just to reduce communication time, but so it is. And if I were running a job, you'd see that this was, became, these nodes entered running status and were not available for use by other jobs. The jobs list, can contain a queue, so you could create a bunch of these to run overnight, so that you had a cluster that was in constant use, and you'd see them running and results filing in. Our training job is the same training script that you saw previously. So if I go and take a look at how this thing did, I can start to see, okay, what happened? Well, it completed. It gives me a runtime. It shows me some of the files that were produced here. So there's a standard error and a standard out. I can go and read and see how this job went. So let's take a look at that standard out. And I can see, in this case, I actually have two workers pinging each other, right? And so they're, each of them is loading, 4 images into memory. And then training begins, and I get an output that looks like what you saw before for my 2 workers. So that's the basic strategy. And I've also run an evaluation job, so so basically performing what that notebook did for us locally before, and have produced some outputs, so some output images in this case. In addition to my standard out and standard error, now I have an images output folder, and it's full of like the predicted labels, true labels, and the input data. So I can go take a look at these. And now, so I'm doing all this graphically, but in the repository there, you'll see instructions for doing this all from the command line as well, which might be a little bit easier if you're trying to maybe run a hyperparameter sweep. Then you know that each job is going to take a while. To be able to pull back all that information and say, okay, help me compare the final results, help me find the model file wherever that wound up being stored that had the best performance. So there are some neat tricks we can do there. So you can see this result is also unusual, but this is after 1 epoch of training, and we're used to 250. Okay, so returning. Okay, so again, since this is not an interactive component, I don't want to belabor it too much, but I want you to know that this will be here if you want to try this out in your own subscription later. The final thing I'd want to mention is how well we did when we were able to scale up. So, we went from having maximum 4 GPUs on a single VM, like the ones that you were able to work with earlier, to scaling up to 148 GPUs. How did we pick that number? This is the number that we need to fit the entire data set into memory. So a relatively large data set provided by Chesapeake Conservancy for this use case. Okay, so how did epoch length decrease over time? So what you would, in the optimum situation, every time you double the number of GPUs, you decrease the training time by half. This is the data parallel distributed training in particular. And that's not precisely what we saw. If that were true, you'd see here a power law coefficient of -1. We got -0.8, so we're still seeing a pretty decent fit here. The fit is applied, however, only up through 64 GPUs, and after that point, what we start to see is that we lose that near linearity in the power law relationship. And so we wind up, in this case, we have too many workers all trying to communicate. Because we're using this protocol, we wind up having to wait for the slowest worker to finish their mini batch before the workers are able to communicate and update the model parameters. So that accounts for why this becomes an inefficient strategy eventually. But even so, it turns out we wind up saving, if we want to use our full data set for training, we wind up saving time by having 148 GPUs, 148 workers, because we're able to load the full data set into memory. Otherwise, we'd have to rotate through our image set, which would involve steps waiting to load those images back up into memory. And in our case, in this geospatial case, that takes so long that it's worthwhile to actually create more workers. So we talk a little bit about how this could be improved further. Different deep learning frameworks will have different options available, but in our case, it's possible to try to decrease the size of messages that workers are sending to each other during these update steps. That might make it more efficient for them to communicate. You can also decrease how frequently they communicate, although there can be trade-offs there. And so you have some other options, but in general, this was a huge speed up for us. We were able to train on the full data set for 250 epochs in, I think, 2.5 hours, which was a huge speed up. Allowed us to get into a range where we could really do some hyperparameter tuning. So Yeah, so that's the basics of this use case from moving from one VM of just debugging the script to begin with to having distributed training on a very large number of workers. So what are the next steps for us? Well, okay. So one thing that we want to do is make that that model available, like I said before, not just with the information on how you can train one yourself, but actually make it callable through a web API. And even through maybe an interactive web app that's a little bit easier for people to take a look at. Now, in this case, it's a little bit odd. The data type that we expect is not the type of image that most people would have available on their own computer, because our model expects information on near infrared as well as red, green, and blue. But because that data is available freely through the government, through this NAIP program, it's conceivable that somebody doing research in this environment would have that and be able to call this API. We've made available sort of an exploratory feature where you can take a look at some sample images or upload your own. We could go ahead and try that out, actually. Let me see. I think I have one file downloaded locally just for that purpose. So here's my 4-channel TIFF. Let's see how it looks. Okay. I guess you want to see the original TIFF, right? In order to decide whether that's a good prediction or not? Okay. Okay, so as I mentioned before, because of that near-infrared channel being treated as transparency, this looks a little bit odd. But you're looking at basically an island, so this what's showing up as rather dull here is actually a body of water. If you compare, I guess, I get them on the screen at once. These predictions, you're actually doing fairly well. It gives proportions of each land type in there. Now, if you want to call this from your own script, we do have information on that REST API available. Because we're trying to limit industrial use, maybe by people in industry, I mean, we do ask that you, request a key, that we can keep track of who's using it and how much. But we have some sample code in here showing you how you'd call that REST API if you want to use it yourself. We're just trying to make this a little bit more accessible as a model so people don't have to have their own GPU locally in order to run it efficiently. So where else are we going with this? Our next step is, I mentioned a little bit about the issues that we face as we try to train a model nationally without having high-resolution labels nationally. And so in addition to trying to leverage those low-resolution labels, we're also trying to create a web app for feedback collection. And this I don't have a live demo to show you. But the basic idea is this is all done through Esri's ArcGIS Online, which is a related product to ArcGIS Pro you just saw, where a user is navigating around, they click an area of interest, and they're shown the predictions from the model currently in the sort of the center here. And they see that there's an error, right? So in this case, there are shadows from these trees that are being treated as if they were water, because those are both cold bodies. So the user says, okay, I want to adjust the class priors and make it less likely that something would be labeled as water. So they slide down water, maybe slide up, built land. And then they're given a few more results. So you see there are 9 results coming up here. This is done by a sort of a unique method for generating diversity in the output of a neural network. Basically, we're applying random dropout to layers in that network so we can get some diversity in the predictions that come out. But the user can then say, okay, of these 9, I think this one is the best. And you can see that now nothing is being predicted to be water anymore. And the user can then say, store that result as a training sample. And it turns out that there are a lot of K-12 classrooms out there that are interested in using this as like a educational unit to, so some means to collect this information. And we also might have interest from local communities to improve their predictions, particularly in the Southwest where our model right now does not perform well. So this is one way that we're hoping to improve that model performance eventually. And a final way that we're using this is basically applying it nationwide using a recent utility from Microsoft called Project Brainwave. This lets you take a neural network model and basically flash it onto an FPGA so that you can create a REST API that is much faster. And so we use this to actually apply the model to the entire continental US in just over 10 minutes earlier this year. So it's a really neat, neat application for showing that we no longer have to wait a long time to get these results out as new data is collected. Now, the NAPE imagery is only collected for each area about once every 2 years, but there obviously satellite data is being collected much more frequently. So you can picture a corresponding model being used in that way, and that's the next direction for us, is making sure that we really can produce time series that allow us to see where there have been recent natural disasters, where flooding is, where deforestation is happening, and phenomena like that. Okay, so that sort of concludes what we have to talk about for the land classification use case. We do have another interactive demo. So are there any questions on this? Or if not, I'll hand over to Bonnie for later. Okay, solid. That's great.
So this one is actually a very short demo, but this is more suited for how this DSVM product is helping data scientists to do a geospatial data analysis using the standard Python tool and the kind of tool that comes with Esri ArcGIS Pro that is already installed in there. So it's very basic, like we'll be going through a map of Florida. So a little bit of background, we'll take a map of Florida and try to see like which regions in Florida seagrasses are growing, and then we'll try to capture some data out of that, try to see like what are the typical features that we see, and if we can predict like what are the regions in other regions in US where seagrasses are very common. So we'll try to predict that, and once we predict it, we have our ground truth to see like how useful that prediction is, and then with that we'll predict in the whole world in the map where the seagrasses are going to more likely to happen. So you are welcome if you want to execute this tutorial along with me. So if you go back to the notebook in GeoBooks.
Oh, it's not showing on the screen.
Oh, sorry. I forgot.
You might also want to close ArcGIS Pro so that you got your GPO back.
So let me duplicate it. Right. So this one, this is the notebook. It's part of our DSVM. I will project it. How can I'm trying to see like, were you able to do a full screen and see both the screens here and there?
I think the problem might be that it's trying to run that on the remote machine. So if you went to another window and tried changing your, I don't know if I'm making sense, but maybe if you change the.
So I cannot do a full screen.
You probably need to not do an extend and then minimize your, not minimize, but
yeah, try changing
file of your window connection.
Yeah. With this remote connection minimized, exactly. Switch from extend to duplicate.
So if I.
The problem is if you do this here, it's going to try to run that command on the other computer, on the remote computer, and that's why it's throwing up there.
Because I need to see while running.
Okay, just don't do extend. Do a duplicate. Put an F7.
So now I do duplicate. Now it is letting me do the duplicate.
Okay, yeah, good.
Now if I full screen, okay, so full screen it is not. Yeah, thank you. Okay, so so what it is actually doing is like we'll be using the typical notebook here, but the major libraries, the Python libraries that are part of ArcGIS are actually these ArcGIS scripting, and ArcPy and ArcGIS.gis. So these are the main important libraries. So what it does, it can seamlessly let me allow to import and export data between my notebook and the GIS map. So this is my GIS map, and say for example I got the Florida map, and these yellow points are where the seagrasses are. So now if I right click and see the attribute table, now if you want to do that, let me start from the beginning. If you want to open that project, it's already there, so I'll start. ArcGIS Pro. And then so seagrass project, because I already opened it, it shows in recent project, but for you if you want to do it, you can go to browse, and it should be in the C drive, GIS demo and seagrass and seagrass. So in the map layer, by default all these layers are selected, but if I want to see, this is my starting point, and I'm just selecting where the seagrasses are right now in Florida. So it takes, this blue thing is drawing, so it takes, so GIS pretty much like it's very graphics intensive, and since this VM we are using for compute only, not like the GIS, poor GIS is not getting enough computing for doing the graphics processing, so it's a little slow. So but I just want to show it here, like if I go to the, it will do the processing, I have to wait a little bit. So while this thing takes time, I'll go back to the my notebook. So then I can just run it. So I have all the libraries initialized. So that means my notebook is ready to communicate with the GIS map, ArcGIS maps. Now the very interesting thing about this ArcGIS Pro mapping tool is like it's a desktop software. So if I want to do some manipulation in the notebook, in the map manipulation, after each manipulation I have to go and open that project and again open it from the GIS desktop. Instead of that, there is another way to do it, like I can actually use online GIS, which is like their portal. So what it does is like the same data that I get from the local GIS, I can actually push and save it into their online storage area. They have their own service. So that is what I am doing here, like I am initializing a GIS instance which will show the map data here in my Python notebook. Then whatever I was trying to show from the GIS map, like on the desktop, like all the Florida data points, they are being loaded in the notebook now. So in the notebook also we can do the same analysis with all the data points and everything. So now the typical geo database, it's actually a GDB in .gdb format. That's what, like where all the geo database is stored, like instead of our regular database. So what we'll do for this demo, we'll get all the features from this geo database, and it will be loaded into our variable called input directory. So from our earlier analysis, like we know what are the typical variables which are actually going to have a lot of predictability on the seagrass probability. So we chose like salinity, temperature, phosphate, nitrate, silicate, dissolved oxygen, and some feature named EMU. These are the main important features. So we'll do some feature engineering here and get those features extracted. Now the thing is that here on this next cell, the interesting thing is we'll read from the map data and convert it into a pandas data frame. So that's the beauty of doing the GIS data analysis here on this notebook. So here we are reading the data from whatever the map data we had earlier, and pretty much tabulating it into a pandas data frame. So now once we have the data frame, we can do the typical data analytic work, like categorizing or breaking or fusing different data types. So that's what we are doing here, and a little bit more data processing, like encoding and breaking a column into 3 different columns. And then the next one, we are actually trying to see like what is the strength of the features in terms of correlating to the probability of seagrass, and we see a good correlation matrix here. Now once we are done with the feature engineering, we are back to a ML classification. This is a standard random forest classification that we have chosen. We can choose other things also, but this is for the demo only to show like we can do it on the GIS data also. So I do a typical classification, split on training and test data, and run it through the random forest classifier. And once it is done, we'll try to predict and see how well that predictor is fitting our data. It might take a couple of minutes, this random forest classification, because we have approximately 700,000 data to test. Yeah, so it's done. So now I'll do the prediction on rest of the data and do the typical like accuracy matrices and see like, yeah, it's actually 99% accurate. And then the good thing is that now we have predicted like where in Florida most of the seagrasses are going to be. So now I can actually write this data back into GIS database, saying like, hey, these are the map points and these are the coordinates where the data where the seagrasses are going to like, and now I am going to write it to the GIS database. But before that I have already existing one, so I am deleting it, otherwise it will not write. So bring output back into ArcGIS database, allowing, so it will write, let me see, oh, it's already exist. So if I delete it, uh,
Yeah, it's deleting something similar, but it's, if you just change that cell that's 42 right now. Oh, yeah, that works too.
this one,
Yeah, that works. Yeah, that works too.
I think I already have it from, because I have another notebook I ran earlier. I just open another one, but you can ignore this. It's already there for the timing. So now I wrote my predicted data back into the GIS database. I want to see how it looks like. So again, I can use that online version of GIS map and see, like, if I use the predicted points into my Florida GDB, how it looks like. So the yellow points are actually where the seagrass is, and the pink point, if I call it pink, yeah, it's actually where it is predicting. Now we got the model, and we are kind of satisfied because it's 99% accurate. So we want to predict for our US data set, like where in US most of the seagrasses are most likely to be. If you are running the same data, similar workflow, I'll just keep running. I'll probably have the same error, I can ignore. So this is the prediction it is going to do for global seagrass now, because we are predicting globally where all the seagrasses are going to be, and so it already exists in this case, so you can ignore that. But now at the global scale, it shows, it will take a little bit of time to load the map, but it shows where the seagrasses are.
Sorry, I didn't get where you pushed. Did you push something? I mean, the result of your predictive model, did you push it to the
So
online version?
no, okay, so the in the online version, those are already pre-pushed.
Oh,
So what I am pushing actually in the desktop version. So I don't know why it is taking so long. Okay, so ideally what you see here, I'm trying to, so like USA data training, if I go and you know, so I am pushing everything on the local database, so those should be visible on the on this ArcGIS Pro. But before this tutorial, actually, I pushed it in online for the ease of showing it on the notebook, so that during the tutorial I don't want to go back and forth between notebook and the GIS. So that's what I did pre. But here, if you want to see it during the training, you have to actually select one of these, and then it will show like where the predictions are and all these things. So this is being populated real time from the training. So this is the last part of the demo where I said, like, globally where it's predicting, like, globally where the seagrasses are likely to be, and this is the map that it has produced on the GDB.
and the pushing to local happens in that cell that.
Yes, so it uses if you want to see here, so this is where
Yeah,
this is where it is actually write locations of segress feature class. So arcpy.da numpy, so that's actually the function to write it back from pandas data frame into the GIS feature set.
Because that cell gave me access denied, GDB system catalog error.
So
I thought it was because I had open, I just open it. Anyway, we can look at it later.
yeah, so I mean that's it. That's the kind of quick demo to show like writing back and forth between the Jupyter Notebook and the ArcGIS in a quick way for GIS kind of data analysis and like typically doing a machine learning model quickly.
Well, we are using ArcGIS mostly for visualization only, right?
For this demo, yes. But for Mary's demo, I think you are using CNTK.
Yeah, actually, yeah, for visualization also mainly in our use case, but also in obtaining the data we work with as research. I know they seem to know more about what they're doing in terms of getting a hold of the data and chunking it in an appropriate way to store. That's not really a expertise of our team, but it was really handy in the sense we needed that particular data type and the header information to come along with the imagery.
Yeah.
It's really appreciated.
All right. So do you guys have any more questions? I can see like what kind of error you are getting like while you are trying to write. I can see.